For convolution in one dimension for 1D signals, fk, hn minus k, k going 0 to n minus 1. You write the function fn, but now you switch the variables to k, and hn becomes hn minus k. So what you have to observe here is k is the index of integration or summation, going 0 to n, 0 for causality starting from the origin, not before, and n again for causality, because you can only look up to fn to get the output GN. You cannot go ahead. So causality implies both these limits, 0 to n. And hn minus k, h is now having minus k reversal with respect to the variable of integration or summation. N is the shift at which the output is computed. Okay? So h needs to be reversed with respect to the index of summation k and shifted by n where the output is to be computed. The index n may be run over a certain range of interest or over all of time for which GN exists. After that, when it's all 0, you stop. So GN is computed for n going 0 to whenever. But we know that when you have two signals of samples n1 and n2, the output has n1 plus n2 minus 1 samples for linear convolution. So for each n, the reversed and shifted version of h is multiplied with the signal f on a point-by-point basis, like a dot product. And multiplication and summation operation together are comparable to the dot product performed over the non-zero overlapping portion parts of the two signals. So let's look at this simple example. Fn is 4, 1, 3, 1. For n going 0, 1, 2, 3, hn is of a different duration, 3, 2, 1. Usually impulse response is decay. For n going 0, 1, 2. So the two signals are of different length. The result G has more samples. We'll have 4 plus 3 minus 1. 6 samples that are non-zero. There could be zeros in between. So the result of linear convolution will have n1 plus n2 minus 1 samples. Okay. So these are the indices. N for the input, Fn, Hn. This is what we defined as an example. K is for the convolution index. K going 0, 1, 2 up to whenever you want. Let's go up to 7. Fk is same as Fn, 4, 1, 3, 1, and a bunch of zeros at the end. So reversal, h 0 minus k, which is h minus k, is from k going 0, 3, 2, 1, 0, going backward. But we don't work on the negative indices. It doesn't matter. We will just write it here. So this is a reversal of 3, 2, 1, 0, written as 3, 2, 1, 0, starting from k equal to 0, going backwards. 1 minus k, you shift. And 2 minus k, shift again. 3 minus k, shift again. 4 minus k, shift again. And you take a product, point by point or sample by sample product of this with fk. Fk is that. In this case, only this sample, one sample will overlap. 4 times 3, 12. Here, 3 times 1 plus 4 times 2, 11. So keep shifting and multiplying those samples that overlap. And finally here, 0, 1, 2, 0. What do we have there? Yeah. 6 minus k. Yeah, the GN will be 12, 11, 15, 10, 5, 1, 0, 0. So for the last two samples, 6. The 6, n equal to 6. There is no overlap. 0 with 1 and everything else is 0. So if you want, I can compute for 7 minus k, 8 minus k, they will all be 0. So these are 0. So you only have these samples, 3 and 3, 6 samples. 4 plus 3 minus 1, and 1 plus n2 minus 1 samples. So this is linear convolution. Whether you call it k or n, it doesn't matter. It's an index. So that's the output of linear convolution. Now you want to do it in matrix notation. You write 4, 1, 3, 1 and put 2 zeros, because we want to allow 6 samples in the output. This is linear convolution using matrix notation. So convolution in 2D. this is the expression we have seen earlier. The range of summation we will allow for the whole range, just for the sake of convenience. You don't normally do that. Your convolution kernel is much smaller than the image. The image could be 1,000 by 1,000 pixels. Your convolution kernel may be 5 by 5 pixels. So your integration or summation is done only over that much. The rest is 0 for the impulse response. The image has non-zero values, but it doesn't matter. For the sake of representation, we will just let it run 0 to n minus 1. If the point spread function is much smaller, you can also let the index run minus m to m. The kernel is of size 2m plus 1 by 2m plus 1. Typically, the kernel is of an odd size, 3 by 3, 5 by 5, and so on. So this representation is convenient then. And then you center the convolution mask on the pixel being processed. You use all neighbors above, below, left, and right within that matrix of the convolution kernel. So then you are making this summation go only plus minus m, the shift, which is applied to h. This is the image, f alpha beta. Okay? The image is of some size n by n. The output is also of some size n by n, but the matrix of the convolution function, the filter, is 2m plus 1 by 2m plus 1, which is much smaller than the size of the image. So the point spread function is reversed, flipped, or reflected in both dimensions. For the signal, we just reversed in time. Now we have to reverse this way and that way. But both of its axes placed on top of the input image at the coordinate where the output is to be computed. A point-by-point multiplication of the values will be performed and added. It needs to be performed for every spatial location for which the output exists or is required, by dragging or shifting the impulse response over the image. In most cases, the point spread function of imaging systems will have some symmetry or even isotropy. So symmetry means if you flip this way or that way, that way, it doesn't matter. So that reversal is not necessary. So then you just use it as a masking operation. Convolution is also a masking operation, but you need to reverse the impulse response matrix before you do the masking. But if the impulse response has symmetry about both the x and y axes, then reversal is not required. So here we have an example, some numbers. I just put some numbers there. And this is the point spread function. You reverse it. So 7, 8, 9 comes this way, 1, 2, 3 goes that way, and then you flip vertically. This 9, 6, 3 goes there, and 7, 4, 1 comes here. So this is the reversed or reflected point spread function. Now that's the image, 1, 2, 1 something. And I have put this reversed impulse response at this position. And you multiply these values 9, 6, 3, 8, 5, 2, 7, 4, 1 with these pixel values 1, 1, 2, 2, 2, 1, 2, 3, 4. You get 79, which goes at this location in the output. And do that all over. You won't believe it, I have done this by hand, and then I put it in MATLAB and checked. And that is correct. If you want, you can also do that. Okay? That's 2D convolution. Now, there is another representation of the DFT. We saw earlier that we could write the DFT as matrix multiplication. But now we will see a slightly different representation. We will start with what is called a circling matrix and see how it is converted to a diagonal matrix by the application of the Fourier transform. A circling matrix has values like this, the same values 0 to n minus 1, shifted, right shifted to the end and also from the bottom to the top. So it's an n by n matrix, but there are only n values that are unique. So that is a circling matrix. So again, let's represent W as exponential j 2 pi over n. W k capital N will be equal to 1. And WKK equal to 0 to n minus 1 are the n distinct roots of unity that form the basis functions of the DFT. We saw the unit circle and those values of W earlier. Now consider this lambda k formed by multiplying the first row C0, C1, Cn minus 1 with this series of W values. W0 is 1, Wk, W2k, so on, Wn minus 1k. So then if you multiply lambda k with Wk again, one of these values, Cn minus 1, will have Wnk, which is 1, so that has no W associated with it. And C0 will have Wk and so on. And multiply again, then Cn minus 2 is liberated of the W factor and so on. So what is happening is a kind of a right shift as you go along. As you multiply by Wk, W2k, Wn minus 1k, these coefficients C get shifted out. So this can be represented as lambda k, Wk is C, Wk. C is that circulant matrix. Wk is the series of these coefficients. We haven't written it there, these coefficients. Wk, it's actually here, that series of values. With this formulation, lambda k is an eigenvalue and Wk is an eigenvector of this circulant matrix C. Now there are n values Wk, k going 0 to n minus 1 that are distinct, and there are n distinct eigenvectors Wk. And then you can write an n by n matrix W as this W0, W1, W so on, and that is related to the DFT, where this nk element W is exponential j2 pi over n nk. This is the DFT kernel 1D. Now this is an n by n matrix. Each one of them is a vector. So there is the property of orthogonality. So W inverse is 1 over n exponential minus j2 pi, that kernel function. W inverse or W inverse W is I, the identity matrix. And the columns of W are linearly independent, so they form this transformation. This eigenvalue relationship, you have a diagonal matrix now. W lambda is CW. So all of these are n by n matrices. Lambda is a diagonal matrix whose elements are equal to these eigenvalues. And you can also write it as C is W lambda W inverse. So this relationship is now interpreted as the circulant matrix we started with is equivalent to a diagonal matrix with the application of the DFT. DFT being applied here. Or this way. Or from the diagonal matrix, by the application of the forward and inverse transforms, you can recover the circulant matrix. So a diagonal matrix represents the circulant matrix. And the values along the diagonal are the eigenvalues of that matrix. So you're extracting a compact representation. So going back.
Similar to PCA type.
Yes. Here we are using the transformation. With PCA, then you select the lambda coefficients that you want to keep and reject the low energy coefficients that you are not interested in, or those that do not contribute much to the representation. So you rank order the lambda case in order of decreasing values and throw away some at the end. Keep 90% or 95%, and you achieve data reduction. Here we're using it in a transformation. So going back to the convolution representation, we had H, the matrix that was formed using the impulse response, and we saw that it is circulant for periodic convolution. So DFT gives you periodic convolution, so we will keep it as periodic. And because it is circulant rather, H can be written as WD We'll call it DH because the diagonal matrix from H, W inverse. DH is a diagonal matrix corresponding to the lambda values of H, the impulse response. So the elements of DH are given by multiplying the first row of matrix H with W and K, which is the DFT. It's a matrix, but the first row is just the DFT. HK is H0 and so on, WK, W2K, that's the Fourier transform. HK is the DFT of HN. So this series of values of H represents Hn minus n. So minus, which is equal to H minus n. So there is a reversal in convolution. That's why you get H minus n. So the series W will have the DFT kernel function. In 1D, having two variables, but you have post and we have the other dimension elsewhere. Okay, it is still blinking. So if you want the usual forward DFT, then switch the variable minus n to m, and then G, the output, is written as G equal to HF. That's what we wrote earlier for convolution. Now G is WD W inverse F. So convolution is now expressed in terms of multiplication of matrices formed using the impulse response and the input image G equal to HF. But H itself is expressed now as a circulant matrix and then further diagonalized using the DFT. W inverse F is the forward DFT of W, this one. And then multiplication by DH. Along the diagonal, we have the Fourier transform coefficients related to the DF, related to H, the impulse response, which is the frequency response, H omega, HK, whatever you want to call it. So this is taking the Fourier transform of the input image, then multiplying by the Fourier transform of the impulse response. This is the inverse Fourier transform, back to the original domain. So the multiplication of the Fourier transform of the input signal with DH corresponds to point-by-point transform domain filtering. And this W does the inverse DFT. Scale factor 1 over n needs to be taken care of. So we have the convolution relationship we wrote like that, H star F, Hn star Fn for 1D, GK, HK, FK, if you take the Fourier transform, multiplying the DFT coefficients, and G equal to HF for convolution in matrix representation, and WD, W inverse F, the same thing, with the DFT included now. So there are these representations, but this is different from what we saw in 367. Let me go back to 367. There, F equal to WFW. In that representation, we were using n by n matrices for everything, and these are images. So F is an n by n image, W is an n by n matrix. So this representation is slightly different from the one that we are seeing now. The one we are seeing now has a signal, a 1D signal. But of course you can convert a 2D matrix to a 1D matrix or array, as we have seen, and then the same thing applies. Okay? So there are these differences in this representation, or multiple representations if you want to call them so. Okay, now the next step. To do this in 2D, F represents the input image now to a 2D filter, and G is the corresponding filtered image. The 2D arrays have been converted to vectors or column matrices. So we will assume all of these have been padded with zeros extended to m by n, and if you don't want m by n, make it n by n, and then These are mn by 1, let's say. The periodic convolution now is given in terms of GMN being this double summation f alpha beta h reversed, but now these indices are mod m and mod n within the period. So the result is also periodic in m by n. So G equal to HF. How do you get that again? So we have to take the matrix H now and see how we can formulate it so that G equal to HF works. So it's a question of formulation. You know what you want to achieve and you define this accordingly. So you create this matrix H by taking the rows of the impulse response matrix and writing them in this manner: H0, the zeroth row, H1, H2, Hm minus 1, and make a circlant matrix of that arrangement. H0, H1, H2, so on, Hm minus 1, shift and shift and shift. The submatrices are given by as Hm, Hm0, Hm minus 1 and so on, and that is shifted in a circlant manner. So the matrix is of size mn by mn, or n square by n square. Each n by n submatrix here, Hm, is a circlant matrix. The submatrices are subscripted in a circlant manner here. And then H is known as a block circlant. It is not circlant by itself, but there are blocks that can be shifted and subsequent rows are formed that way. So it is a block circlant matrix, but this is circlant. So this is formed using the mth row and all the columns of that impulse response. The same Hm, different elements. Okay? So let's look at an example. I spent a lot of time to prepare this long ago. Fmn, let's consider this some number, 1, 2, 3, 4, 5, 6, 7, 8, 9. Just put some numbers, and I padded with zeros to make a 5 by 5 matrix. So the image has non-zero pixels only over a 3 by 3 region. And let us take the Laplacian. 1 minus 4, 1 all the way around. We saw the Laplacian earlier, right? So pad that with zeros to make it 5 by 5. So everything is 5 by 5. Now the origin of this is in the middle. The origin of a matrix typically is taken to be that. So we have to rearrange this and put the origin there. So we get this matrix, minus 4, 1, 1, but what was above comes here, what was here goes there. Okay? So Hmn needs to be rearranged this way. And if you do G equal to Hf, you get this. You could work this out. There are negative values because the Laplacian is taking derivatives. Okay? And it's a 5 by 5 output. The images were 3 by 3, so 3 plus 3 minus 1, 5. There are a few zeros, but that doesn't matter. So what does H look like? Yeah. So this is the output G. This is the input image F. This is the block circlant matrix made using the Laplacian 1, 1, minus 4, 1 and minus 4, that's all. So how do you get this? You take the first row, all zeros, second row, 0, 0, 1, 0, 0, third row, 0, 1, minus 4, 1, 0, and so on, and make circlant matrices with each row. The first one is with that minus 4 Sorry, not that. Not with this one. With the shifted. The first one is minus 41001. So take that, and that is the first row, and circulant matrix with that. The next is with the next row 100 and 111 just shifted. Next has zeros, no problem. Last one had 1 there. And this is now block circulant, so shift this whole block there, and that there, and that comes here. Next shift this here, right shift, the whole block. So that is the block circulant matrix for 2D convolution. The input image is this, 01230, here, 000, 01230, and 654, and 789, and 0. One row at a time, written as columns. And the output is that. Now we have to just rearrange this output, write that as the first row, second row, third row, fourth row, fifth row. So that is the output. You just have to recompose it. Okay? I'd never seen an example like this. I sat and worked this out by hand, and it took me hours to do that, and then checked with MATLAB. Is that clear? You were asking a question how to do linear convolution with circular convolution. We saw with, there were 2 questions earlier. So we saw in 1D and 2D now. So how do you diagonalize this? That is possible. We won't go into the details of this. There is a paper I have referred to in the book. By the way, these notes don't have references. We don't show references in lectures. The references are all in the book. So all citations have been. I wrote the book using LaTeX, and these notes are in LaTeX, and I got a style file made to turn them into this format. So all the equations are retained from the original in the book, and all the figures are retained. I had to reformat the figures. But the book has all the numbers, equation numbers, figure numbers are the same. The references are in the book. If you are able to get the book from a library somewhere, I've given that old book to IISc Bangalore Library, PS College, Mandayam Library, and a few other places. But don't buy that because it's outdated, 2005. The new book will come next year. If you can find it somewhere, there'll be some unauthorized digital copies floating around. You'll be able to find it. Don't tell CRC. We have told them, actually. They know, of course. But you have all the equations here. I have added 3 files, by the way. Initially, I missed sending chapters 7 and 8. I don't know if we will do chapter 7 and 8, or there is a combined reduced version called texture analysis. So there are 3 more files. Please go to that location and download those files. Depending on the time, we will see if I will do 7 and 8 in detail using these notes, or a compressed version in a different format. We'll take a look at that later on when we get there. So how do you diagonalize this? You consider the same Fourier transform. Now in WMKM is exponential j2 pi km and ln in the row and column matrices in the input and output domains. So define a W matrix that is Mn by Mn. For the 1D, we use N by N. Now you use Mn by Mn. Containing M square partitions of each of size N by N. One row of the impulse response at a time, as we saw just now. So the kmth portion of WKM is given by WKM, this function, times Wn. Wn, this is an N by N matrix, given by the DFT coefficients. W inverse is also Mn by Mn, and it has partitions N by N, M square of them, and the partitions are given by this W inverse Km is W, this function inverse of that, Wn inverse. So similar to what we saw in 1D. I won't read all of that. So again, you can show, I won't go through that proof. There is a paper I have referred to in the book. H is WD, W inverse, like in the 1D case. And we have these representations of 2D convolution, like 1D. GMN is HMN star FMN, and you can expand that with the double summation. In the Fourier transform, it is just multiplication of the coefficients of the Fourier transforms of H and F. G equal to HF, or G is WD, W inverse F. The same thing. So if you've seen the formulation in 1D, it's the same thing here by converting the image into a column vector or column matrix. So considering an n by n image, the n square by n square DFT matrix is different from the other n by n matrix we saw earlier. We saw two formulations. So it is different from the n by n DFT matrix where we wrote it as WFW. The image matrix F is of size n by n, whereas when you represent it as a vector, as a column matrix, it's n squared by 1. So there are multiple representations of 1D and 2D that you should watch out for in this discussion. So to end this part, why did we go through all of this? By the way, this representation has been discussed in detail by an old book on image processing by Hall, E.L. Hall, that I used as the textbook when I started teaching image processing in 1982. Gonzalez and Woods had a small book at that time. It was Gonzalez and Wintz. But this book Hall's book has more mathematics had at that time. He didn't come up with any new addition. All these details, mathematical details, and I found that interesting and retained that and expanded on that in my book also. Others have not gone through all of this information in as much detail. Some books have had it and later editions have dropped it. The tendency nowadays seems to drop all the mathematical niceties and just show pictures. In fact, there is a very big book called a handbook, Image Processing Handbook. I won't name the author. It only has pictures, beautiful pictures like an album. No equations. So one of my colleagues, when I gave these courses, was telling me, well, that book has all these pictures and describes image processing, but there are no equations. We need all the equations in order to understand how it is done. My students in Calgary have often asked me, well, why do I need to know this? It's all available in MATLAB. So I tell them, do you want to be a button pusher for MATLAB, or do you want to know and do what is behind the button and do something bigger and better so somebody else will push the button for you? So I don't want to be a button pusher. I want to know what is there behind the button and possibly design something bigger and better. Not making money. We didn't make money out of that. We add to the knowledge base. Maybe some will make money out of that. So, yes, it is important to know this. I hope I would say, some people say, did you enjoy it? It's not for enjoyment or entertainment. It is to learn something. I hope you find it beneficial, let's say. Or it may benefit you sometime later. So why? Now you can take derivatives. When you have F transpose G or G transpose F, take the derivative with respect to F, you get G. Like regular derivatives, because they are point-by-point multiplications, the derivatives will apply on a point-by-point. So the same vector is reconstructed as, note that this is partial derivative with respect to each element of F on each element of the output. And when you have F transpose WF, you get 2WF. Taking the derivative with respect to F, not W. W is the transform matrix. You don't take the derivative with respect to that. But the input variable F, the image or signal. So optimization of filters may be performed using matrix representation of images and image processing operations. Okay? any questions? I've been giving my own comments in between. I should have waited for your questions and then said some of the things I said. Any questions about what we have done so far? Let's take a little break and have a discussion if you have any.
Eigenvalue setting come down here. So here the eigenvector is kind of fixed for all the thing. Succulent matrix can vary because Fourier basis is fixed for.
Yes.
But in the PCA, the eigenvector will change.
No. The eigenvalues are related to the impulse response matrix. The eigenvalue DH that we wrote, that is related to the impulse response values, not the DFT.
So the Fourier coefficient will change.
The Fourier coefficients are in the other matrix W, WD, W lambda W. So the D matrix has the eigenvalues of the impulse response matrix, which will change depending upon your filter or operation, the kernel function, not the Fourier transform or Walsh-Hadamard, whatever. That's in the other W inverse or AA inverse, that matrix.
So the Fourier basis will convert any circulant matrix into a diagonal matrix.
Yes. But the circulant matrix was derived in this case from the impulse response.
From the
Yeah.
All the filters, all the transforms used in image processing, all are having these properties like separability or tonality.
No. The separability and so on, they apply to the transform, not the filter. The transform, the DFT, is separable. You may have other functions. If you use some other function, I can't think of something else. If you use some wavelet transform with some wavelet, you may not have the separability and symmetry. But here, because you're using complex exponential functions, sinusoids, then separability and symmetry comes in. Okay?
What are the major advantages of having the separable orthogonal?
In terms of implementation and computation, a two-dimensional summation or integration is separated to a product of two integrals or summations on individual variables. But the transform, each transform, even in 1D, has two variables, one input, one output. J2 pi nk. N is for time, k is for frequency. Nk, ml. They were together as nk plus ml. When you separate, you get two separate integrals or summations. That means the 2D transform can be computed as a series of 1D transforms. So if you have an m-dimensional signal, then it is m 1D transforms with the DFT. If you design some other transform, you might not have these properties. The DFT, the Fourier transform, has these properties. That's why we're still using it. When was it? Fourier was in the 1800 something. You can check 1850 or something, 1840. So 160 years later, we are still using his transform. It's working. The others, some have come and gone. So when you have these properties, there are some advantages. And interpretation of the frequency content is easier, and we can think in terms of sinusoids, tones. For 1D, various frequencies are tones that we can generate. So we can connect with those. 2D, it's a little bit harder to connect with 2D sinusoids. But 1D, it is easy. So that transform has lived on. The separability symmetry facilitate representation and computation. Nothing to do with the filters, but with the transforms. Okay. So now was there something? No. Okay, let's look at the Wiener filter. The Wiener filter is a linear filter designed to minimize the mean squared error between the output and the input, which is not known. You have a distorted or some representation of the input that you obtained. It was degraded somehow. and you want to estimate the original. So you're not simply applying some filter and telling, well, this is a better picture than what you gave me, but you're trying to estimate in some optimal sense. The filter output is an optimal estimate of the original undegraded image. In what sense? Mean squared error sense. So it is also known as the linear minimum mean squared error, LMMSE, or linear mean square LMS estimate. A few different names for the same thing. It's a very popular filter. It's been around for 60 years in 1D and also in 2D. Not as long in 2D, but in my signal processing book, I have given the details of this derivation in 1D and applications to biomedical signals. So here we will use this representation G equal to F plus eta. We are considering only addition of noise. There is another representation with G equal to HF plus eta. H is an impulse response that is blurring the image, and then noise is added. Typically, when you acquire an image, there will be some blurring. My camera is not focused, there is some turbulence, and something is happening, so there will be some blurring. And then noise gets added due to all these instrumentation and the ambience. So G equal to HF plus eta, but then you require an inverse filter to remove the convolution H factor. That I have dealt with in a different chapter on image deconvolution and restoration. There is a Wiener filter for that also. But we won't go into that. If you're interested, you should refer to the chapter on deconvolution. But here we will look at noise removal only. The degradation is original image plus noise is what you have observed, or recorded, or captured, or given to you. So what you want to do is find F tilde. Tilde is used to indicate an estimate in some sense. Some books use the hat. I didn't use the hat because the hat is also used for the complex Kepstrom. So I kept the hat for the complex Kepstrom, and here we use the tilde to represent an estimate of F. It's LG. L is some filter. You apply some linear filter. We only know linear filters at this time, using LSI or linear shift invariant system representation, using all of what we have seen so far. So apply some filter G. You don't know what that filter is to get that estimate, F tilde. Now F and G are n squared by 1 matrices, formed a row or column ordering of the n by n images. And L is an n squared by n squared matrix in this formulation. And we have seen that formulation also earlier. The optimization criterion says minimize the mean squared error, epsilon square, which is expectation of F minus F tilde square. So the difference between your estimate and the original unknown image should be minimized in this sense, which is the square error. So it is called minimum mean squared error. Because the filter is linear, it's called linear minimum mean squared error filter. For the formulation to get the cross terms here, the energy of the error is defined not using the dot product, but as the trace of the cross product F minus F tilde, F minus tilde square, tilde transpose. We saw this formulation earlier to get the energy of an image. So then you get all of these terms. You take this and expand, you get F transpose minus F tilde transpose and all of that. I won't read all of that, it's too much to read. And the transpose of F tilde is G transpose L transpose. F tilde is LG. Now the transposition is, each one is transposed and the whole thing is reversed. G transpose L transpose. G is F plus eta times L the filter. So now you expand each one of them. So you get all of these factors. So take each of these and put G's f plus eta there. And expand these, there is no g here, and take this. And you get finally this expression. Not finally, this f tilde transpose is this expression. Now, because g is f plus eta, you are getting these combinations of noise and signal, with one of them being transposed, and the noise also. Okay? So, go back here. We wrote g equal to f plus eta, and f minus f tilde. F tilde is Lg. G is f plus eta. And the mean squared error is that it has all of these terms, these 4 terms. Expand each one of them using g equal to f plus eta, and f tilde as Lg. And finally, each of these terms will turn out to be these quantities. So what you need to observe is that we have these combinations, the cross terms are coming now between the noise and the signal. Now we have a trace here, expectation and trace. In this matrix, you want to add up all the trace elements along the trace is the sum of all the diagonal elements, and you take the expectation, but then you can reverse that. The trace of a sum of matrices is equal to sum of their traces, so expectation and the trace may be interchanged. So take the expectation inside and apply to each of these quantities that you have. Expectation of FF transpose is autocorrelation. We have seen this earlier. We started with these definitions. And FF tilde, you get phi f with L. F tilde is L. The transposition is in the transform. Filter is included here. Fn and where is the other one? It's not here. Okay, this is 0 because f and n are assumed to be statistically independent. This is an assumption made in Wiener filtering, that the noise and signal, when you project them, the expectation is 0. The expectation of n is 0, of eta is 0. Expectation of f tilde f is that, transposed. So L phi f. And this big expression we had here, you take this and that, and these cancel out. So you get only these two terms, L phi, L transpose, and the transposition of that, or rather with the eta, noise. Autocorrelation of signal, autocorrelation of noise, of the original, which you don't know. Expectation of eta, eta transpose is phi eta like that. Okay? You should work this out once and you will know. You have a question? No? No. Okay. Now you have the mean squared error, epsilon square, as trace of all of those put together. The autocorrelation function phi f is symmetric. The autocorrelation function of noise is diagonal because the samples are uncorrelated. The cross correlation terms will be 0. So the trace of phi f L transpose is trace of L phi transpose. So you get now the trace of autocorrelation of the original image, that with the filter, and that with the filter, autocorrelation of the noise with the filter. L is the filter you are designing, Wiener filter. So now the mean squared error is not a function of f, g, and eta that it was before, like this. It had a f and eta, but we don't know f, the original image. And you don't know eta, you don't have one noise, you don't deal with one representation or observation, you want the general statistics. What are the statistics? Phi f, phi eta, that's all, autocorrelation functions. So now, the mean squared error is not a function of the images themselves, but on their statistics, function of their statistics. And the statistics are simply autocorrelation function. So you need to differentiate that with respect to f and find out what is the optimal L. So differentiate, with respect to L, and then take this partial derivative with respect to L. That has nothing. This has 2 phi f. This is 2 phi f. This is autocorrelation. So you get minus 2 phi f to L phi f to L phi n, and the Wiener filter is that. Autocorrelation of the original image that you don't have, and the inverse of this combination of the autocorrelations of the original image and phi of and noise. So the filtered image is phi f over phi f times phi f plus phi eta inverse times g, the given distorted image. So that's the optimal Wiener filter, optimized in the sense of minimum mean squared error, linear, assuming that the noise and signal are uncorrelated. And did we see anything else? No, that's all. Now, what we need are these quantities. We don't need the original image, of course. That's what we're trying to estimate. We don't know. Noise, you need to estimate the statistics now somehow. Autocorrelation function. And let's see how we can modify that a little further. So now inversion of that matrix could also be a problem. It's a large matrix, n squared by n squared. So inversion is easier if the matrix can be written as a product of a diagonal matrix and a unitary matrix, as we saw earlier. So the Fourier transform helps in that. So phi eta is diagonal if eta is uncorrelated random noise. So it's already diagonal, no problem. What do you do with phi f? Here we start making some assumptions. In most real images, the correlation between pixels reduces as the spatial shift increases in most real signals. If the signal is periodic, then the autocorrelation function will keep peaking whenever the same period appears. But in a real life signal, take a picture outside or any natural signal, voice signal is periodic, so not that. Some other signal, then as the shift increases, the autocorrelation function decreases. And very soon it will go to 0. So in most cases, autocorrelation function is a decreasing function, and for large shifts it goes to 0. So then phi f is banded. There are many, many zeros, and may be approximated by a block circlant matrix. It's an approximation. Then if it is block circlant, phi f is W, this capital phi f, W inverse, where phi f is the Fourier transform of the autocorrelation, which is the power spectral density function. Fourier transform of autocorrelation is power spectral density. Similarly, phi eta is W phi, capital phi. This is the power spectral density of noise, W inverse. W is the DFT matrix. So now we have simplified in the sense we have diagonal matrices. And the diagonal matrices, as we saw earlier, contain the Fourier transform coefficients of whatever it is you derive it from. Fourier transform of the autocorrelation, that is the power spectral density. Fourier transform of the autocorrelation of noise, power spectral density of noise. This is power spectral density of the original process that generated the image, not the given image. So then, F tilde is this big thing now with the DFT taken out. W inverse DFT, phi f, autocorrelation of, the power spectral density of the image process, phi eta, power spectral density of noise, inverse is there. W inverse is the forward Fourier transform, and G is the given image. So take the Fourier transform of the image, multiply by this filter, take the inverse Fourier transform. So W inverse G is GKL, Fourier transform of GMN. Phi f, W inverse, this low, small phi f, W is SFKL, pass spectral density of Fmn. Phi eta is similarly S eta KL in array format that we are familiar with. Then the Wiener filter is this. F tilde in the frequency domain is SF over SF plus S eta G. This is how it is implemented in 1D also. We can, through a different formulation, we can get this in 1D that you can see in my other book on signal analysis. Or divide by SF, you get this. So this becomes a little easier for us to interpret. We know pass spectral density and frequency domain functions a little better than autocorrelation matrices and the pass spectral density as a matrix. So what does this say? When there is no noise, this is 0. And the output is equal to GKL. Nothing is done. So if there is no noise, the filter just passes the signal on a component by component basis. That is for every KL in the frequency domain. And wherever the noise is high compared to the signal power in the frequency domain KL, if the noise is large, this becomes large, and 1 over a large number, the gain is reduced. So wherever the noise is high, the gain is reduced. Wherever the signal is strong or there is no noise, the gain is equal to 1 or close to 1. So GKL is modified on a frequency component by component basis by a varying gain depending upon the noise to signal ratio in the denominator. So that is the Wiener filter. It depends upon the second order statistics of the processes generating the image population that you are dealing with, not that specific image, than upon single realizations. I mentioned earlier that it is, when we looked at the statistics of images, I said the probability density function and autocorrelation, they need to be computed with an ensemble or population of images of the same type. Mammograms or CT images of the abdomen of pediatric patients or male, female, and so on. So there must be a categorization. You don't mix CT with MR and other things. So if you're going to apply this filter to mammograms, you compute the autocorrelation function of a number of mammograms and average them and maybe fit a model, usually Laplacian model. Autocorrelation function decreases, Laplacian models fit well. And you just need the sigma, that parameter, the width of that function. One parameter that you have to store. If it is something else, some other function, a few parameters will help you save that function as the function SF or S eta. S eta typically is flat. If it is not flat, then you estimate it. So this is estimated from, let's say, a number of mammograms. And if you fit a model, the advantage is you just need the model parameters and say, if your input is mammogram, use this. If your input is CT image, use that. If it is some awkward function that you cannot model, just save that whole thing. As eta, you have to estimate noise. And you could estimate noise from the given images too by saying, okay, in this portion there is no image, so I'll take such portions from a number of images, take the autocorrelations and average, and then get the pass spectral density or keep the autocorrelation. Typically it'll be flat. If not flat, whatever it is, parameterize that and save it. So for each application, you could save either the pass spectral density models or autocorrelation models and apply the Wiener filter. You don't redesign the Wiener filter for every image of that category. So the gain of the Wiener filter varies from one frequency to another in accordance with the SNR, the signal to noise ratio or noise to signal ratio, as a function of 2D, UV or KL, frequency space. Gain is high wherever the signal SF is strong as compared to the noise S eta, high SNR. Gain is low wherever SNR is low. Gain is equal to unity if the noise PSD is 0 at that point. The Wiener filter has nice theory. We study it in communication theory, DSP, and so on, in 2D also, but there are limitations. It is not adaptive. It is linear shift invariant filter with one impulse response or one frequency response for the whole image. For a mammogram, fine, there is some variation, but not that much. If you take a chest X-ray image, we have ribs and lung parts and the heart and so on, the frequency response is different. In CT image, there are more parts that are substantially different. So you need a spatially adaptive filter in such cases. Or you take an outdoor scene, your trees and vehicles and people and so on, then one filter for the whole image will not work well. It will give you some image. You may not be happy with the result. So it cannot adapt to the image and spatially. For the whole image, it is one filter. It can suppress noise, but it is likely to blur sharp features and edges. The noise will control the filter. But when you have sharp edges or nothing, or some other smooth variation, the filter cannot change. In the frequency domain, it is one shot point-by-point multiplication. In the image domain, it's a small, you can reduce it to a small mask, and you're applying it as convolution. When you're moving the convolution mask across the image, it is the same mask being applied everywhere. So there could be some detail here and some other detail here, but the filter does the same thing. So it is not spatially adaptive. The design of appropriate signal and noise PSD models or autocorrelation models is difficult in practice, and if you use poor or inappropriate models, the results will not be good. They're optimal in some sense, but if the models are not right, then the filter is no good. The assumption is that the noise and image processes are second-order stationary processes. That is, you're only using autocorrelation and power spectral density. So mean and variance do not vary from one image region to another, which is not true in most cases. So the entire image is characterized by a single spectrum of PSD, and most real-life images don't satisfy these assumptions, and we need spatially or locally adaptive filters. So here is an example. The test image is one of those shapes images. We added Gaussian distributed noise. The image PSD, it's a little difficult to model this. I modeled it with a Laplacian function with sigma equal to 5 in the PSD, the power spectral density in the Fourier domain. And noise was modeled by a uniform function. So that's the original image, the noisy image. Sorry, I shouldn't press that. The Fourier transform of the original image, the Wiener filter. The Wiener filter, because the model is saying image plus noise, the Wiener filter to remove noise has to be a low-pass filter. So it is a low-pass filter, high gain here, gain reducing with frequency. That's the output, blurry. Noise has been reduced. Okay, compare with the original there and the noisy image to the right, and noise is reduced, but the edges have been blurred. So you want an adaptive filter, and there is an adaptive filter we will see next that gives this output, where the edges are sharp, but some noise is remaining inside these objects, as you can see. Inside this white box, you can see some patches of noise here. So adaptive filters also have problems. It's not like adaptive filters can do wonders. They can retain the sharpness of the edges, but inside it takes some time to adapt as the filter moves. And while it is still adapting, the results may not be good. We will see that filter next. Any questions about this? No?
Smoothness is because of what? The smoothness because of what?
Because of the Wiener filter being low pass. You see in the second row on the right side, that's the Wiener filter in the frequency domain. The gain reduces with frequency. In high frequency zones, the noise is stronger than the signal. The signal actually has sharp edges. In this case, the images have sharp edges. But the model for the pass spectral density I used is a Laplacian.
This is because of the second order statistics or something we use only second order statistics?
Yes, true. The Wiener filter uses only second order statistics, but the problem could also be with the model for the signal that I put in. I don't know how to model all of those shapes, right? There's a mixture of so many shapes. So I just put a Laplacian like that, which is not a good model. So it also illustrates what I said earlier. If the model that I put in for the autocorrelation or the pass spectral density is not good, the result will not be good. How do I model the pass spectrum of an image like that? I could possibly take a number of such images under noise-free conditions and average their pass spectral densities and build a model and keep that. I could have done that. I could have generated a number of those pictures. We have a few, and average their pass spectral densities and fit a curve. That is possible. I didn't do that. So if my model is not good, my output will be affected by that. I said the frequency contents of my signal decrease as a Laplacian function. In this case, they don't. Because I said that in the model, and I said the noise is constant at all frequencies in the PSD, pass spectral density, then it says do a low pass filter like that. That has suppressed the edges, blurred the edges. If I can put a better pass spectral density model, I may get a better result.
So in this case, we don't assume the desired output, right? So we don't assume any desired output, right? How we can compare with the least squares and this?
No, it's a least squares filter, yes.
Least square filters.
Yeah, it's a minimization of mean squared error. That's what we said earlier, right? We formulated the error and took the squared value and the mean of that.
That F is the desired one. F tilde is
F is the desired. F tilde is the output of the filter. Okay.
But you said right, the F transpose is the autocorrelation. Usually the autocorrelation is formed by the data matrix, right? Data using the data. Autocorrelation matrix is usually the data matrix.
No, this is expectation of F transpose is of the original unknown image, not of the given image. The given image is modeled as G is F plus eta. So the autocorrelation is of the original process that generated the image, not of the given image.
Here everything has to be estimated.
Yes. So that we don't know the original image, of course. So we need to build a database of clean images of that type and then get their pass spectral densities or autocorrelations and average them. I didn't do that. I just put a Laplacian model. But that phi f is the autocorrelation of the original process that generated the image of the type we have on hand. F tilde is the output of the filter.
In communications, we assume the time being the data is available. Like desired is out.
That's different. That formulation is in my other book, where eventually you replace that with a shifted, delayed version of the input. You assume the signal is available, And then you say, well, I don't have the signal, so I'll take it to be the input with a delay.
Here the formulation is
It's different, slightly different. Yeah. The assumption is different. In my signal analysis book, I have used that definition, where it is assumed that the input, the original signal is available, and you go through the whole derivation and then say at the end, well, I don't have the original. What do? I say the original is equal to the current signal with a shift. That is also a strange assumption to say, because the given signal is noisy. So the shifted version is not noise-free. That's an assumption made there. Here it's a slightly different assumption in this formulation. Okay? Any other question about this? Okay. You said 12:30, right? Okay. Okay, adaptive filters now. We will see a number of them. I'll go through one formulation and leave the rest. There is a local LMMSE filter, like a local Wiener filter. How do you make the Wiener filter adaptive? On a pixel by pixel basis. But then you have to remain in the image domain. You can't go to the Fourier domain when it is not, not spatially invariant. If it is spatially variant, you cannot go to the frequency domain. So the adaptive local statistics based filter to obtain the same formulation of a linear minimum mean squared error, LMMSE is the same, but put another L that is local. Lee designed this filter. The degradation model is the same as before, G equal to F plus eta, but now we remain with this Mn because the filter changes with Mn. So data will be shown in this format to indicate the pixel position where you are putting the filter, and the filter depends on that. F is a realization of a non-stationary random field characterized by spatially varying statistics. Now it is generalizing. The filter can adapt to an image with different characteristics over space. So no frequency domain then. Noise process eta may be either signal independent or signal dependent, and non-stationary, don't care. It doesn't make any assumptions about that. So it says compute at every pixel location Mn an estimate f tilde of the original f by applying a linear operator to Gmn. So what is a linear operator? You have two scalars, a and b, that are variant, spatially variant. So f tilde is amn gmn plus bmn. Just ax plus y, linear. So not ax or not ax plus y, I should say ax plus b or something. So a is a coefficient, b is a coefficient. It's a bias at every pixel. This is just a multiplier, a weight factor. To minimize the local MSE, f tilde mn minus fmn square, and this bar says average in some way. It's not the expectation operator, it is some averaging somehow. And we will see that at the end. Okay, the formulation, just AG plus B. A and B are two coefficients, but they're all functions of Mn. So then this epsilon square is AG plus B minus F square, an average of that. Take the partial derivatives with respect to A and B and set them to 0. So take the partial derivative with respect to B, so you get this quantity. That bar remains undefined. And then you get B is F bar minus A G bar. I won't read the Mn. And put that and get epsilon square, differentiate with respect to A, set it to 0. You get that quantity. And now this has so many things here. You get all these cross terms. You have to work out all these terms. F bar, G bar, F bar, G bar, F, and all those things. And here AG and AG bar. So now to simplify it, you say, okay, G minus G bar. G bar is like a mean, mu. So the signal minus mean square is variance, averaged. That is like expectation, let's say. So this is variance of G. G is the given signal. But at the local point, Mn. That's a local variance of G. And G minus G bar, F minus F bar is sigma Fg, the covariance between the two of them. So this says then Amn is sigma Fg over sigma square G, a ratio of the covariance to variance. So F tilde is F bar, you put them all together, sigma Fg over sigma square G, G minus G bar. So these are statistical entities based on some local window, because you have to make them a function of Mn. It's not computed for the whole image or population. It is computed for that image, the given image in that window. So you are substituting later on expectation and statistical processes with local averages. We have done that with time signals and the time temporal statistics and spatial statistics. So now we are using spatial statistics, local, not for the whole image. F bar is a mean at that location. But F is the original, we don't know that. Fg, we don't know that. F is unknown. So we need to manipulate this further. So the true statistics of the original and corrupted images, as well as their joint statistics, sigma Fg, are unknown in a practical situation. So Lee said we will estimate them locally in a spatial neighborhood in the given image itself, and then formulate a local Wiener kind of a linear minimum mean squared filter. So use a rectangular window at that location. 2p plus 1 times 2q plus 1. So it's an odd sized window, but the window size could vary to be adaptive. So it's not 3 by 3 or 5 by 5. We'll let it be a rectangle of some size to be defined later. So mu g, the mean of g, is given by the average of g over that window. Okay, it's a big equation, but it's just averaging of g, the given image, over that window, centered at Mn. So it changes from pixel to pixel. Sigma square g is g minus mu g square and averaged. Okay? Local statistics. The filter parameters are functions of space. They are space variant. So it is an adaptive filter that is space variant, and hence you cannot go to the frequency domain. So now F tilde is mu g, sigma square g minus sigma square eta divided by sigma square g, g minus mu g. All functions of Mn. So this is also known as the Wiener filter or local Wiener filter. It looks like the Wiener filter, but it varies with the indices Mn. It is locally adaptive. MATLAB calls this the Wiener filter. LIM also calls this the Wiener filter. It's only because of that minimization of the squared error. Otherwise, it has nothing to do with Wiener. So there is some similarity. But the interpretation is slightly different, as we will get to the end. So this LLMMSE, local linear minimum mean squared error filter, is spatially adaptive and non-linear because of the space variant estimation of the parameters. Depends on the image, so if you add two images, these statistics will be different. Okay, let me get to the interpretation of this. This is the filtered image, F tilde, estimate of the original. Mu g, g is the given image. It's a local average in a window, whatever size you choose it to be. G is the given image at that pixel, minus mu G, subtract. This is the weighting factor. Sigma square G, the variance of G, the given image at that location, minus sigma square eta Mn, the variance of noise at that location, divided by sigma square G. Sigma square G you can compute from the given image. How do you estimate sigma square eta as a function of space? That is another question. Typically you would assume that to be constant. You would assume the noise is the same all over the image. So if you can measure the noise from somewhere in the image and get its variance, get a bunch of pixel values from somewhere where there is no signal, and say, okay, that's my variance. And I'll just assume the noise is the same throughout the image. That's a reasonable assumption. It is not reasonable to assume that the signal variance is the same throughout. That is not reasonable. But noise, it's okay. There are other ways to estimate that also if you want as a function of space. So this is some factor, let us say. You could say by removing the variance of noise from G, which has signal and noise, you are getting an estimate of sigma square F, the original variance of the original, in a way, divided by this. So this, what is mu G? Mu G is a local mean, which is like a low-pass filter version of the given image. When you take the local mean, the 3x3 mean filter we saw, it is a local mean, and that is a low-pass filtered output of the image. So this is a low-pass filtered output at that location using a little window. And what is this? The signal minus the low-pass version. 1 minus low-pass is high-pass. So this is a high-pass version. Edge enhancement is being done here. So this is blurring, this is sharpening. Low-pass filter, high-pass filter. You are getting a combination of low-pass and high-pass filter controlled by this gain factor, which changes with the local statistics over the entire image as you go, with the filter window running across the window, across the image. So that is how it is adaptive. It takes a combination of a low-pass filtered version and a high-pass filtered version of the given noisy image and gives you something with enhancement with noise control. So where you have sharp edges, it will try to preserve the edges. Where there are no sharp edges and only noise, it will suppress noise.
This is done by pixel.
I'm sorry, you have to speak up a little.
No, this is done by pixel by pixel.
Yes.
Pixel.
Yes.
Pixel by pixel by pixel.
That's why the filter is, everything is written in terms of MN.
And why can't we take like a window and
Yes, these are all computed, these are computed using Windows.
But what is the typical window size?
That's up to you. 2p plus 1 times 2q plus 1. You can let that window change, we will see that. You can let the window adapt.
If you take a bigger window, the statistics will be changed.
Yes.
Non-stationarity comes into picture.
This is non-stationary already. This is not
we assume stationarity and we apply linear feature. That's what
with the Wiener filter. This is not stationary. Here we didn't say, we said specifically the image is non-stationary. Even the noise could be non-stationary. So there is no stationarity here. Everything is varying pixel by pixel. And the statistics are estimated using a window, local window of some size. We didn't say what the size is. Actually we said, I think, here. It is 2p plus 1 times 2q plus 1. Whatever p and q you want. But there is another filter we will see where the size of that rectangle is adjusted. There is an adaptive rectangle window. And we have our own adaptive neighborhood filter. So this can be changed as you wish. But it's a local statistical measure. So it is non-stationary. It is non-linear. It is adaptive. Okay? There is a matrix derivation. My colleague Mihaichuk in Bucharest, he was with me for some time. He gave me this. So you can go through that same formulation using matrix representation. F is AG plus B, and go through all of this. go through all of this, and finally you get the same thing like this. Low pass filter, high pass filter, that's the gain for the high pass filter. I'll let you read that later if you wish. So there are some variations on this. We'll skip that. In some variation, that window is split. The window that you use to compute statistics may be split vertically, diagonally, up, down, left, right, and so on, depending on local edges. If there is an edge present, this method, refined method, says don't compute the statistics over this entire window, but use only one part and compute the statistics using that part, and don't blur across edges. So you have to estimate the presence of an edge and its orientation by using gradient operators, which you can do, of course. And then the window of some size, here we have assumed it to be square so we can show the split. You use statistics from the side where your pixel is sitting, or an appropriate size, or part of it. There is another version where these sigma values are updated. Sigma eta of the noise is updated. I won't go through that. And we will stop here, but let me go back and show you that output. The images have been put together for comparison. So we have the original and noisy, as we saw before. The output of the fixed Wiener filter, but my signal or the original model of the original pass spectral density is not good. It's a Laplacian, it's not good. In some cases I have done something and I could say I didn't want to spend too much time to find a better model, or I also want to say what happens if you don't use an appropriate model. If my model is not good, I may get a bad result, and I don't want to blame Wiener for that, of course. But the adaptive one is this. So there's a big difference. Sharp edges are maintained. There is some smoothing compared to that, compared to noise here and noise inside the white big square or that triangle. A little smoother. Edges are sharp, but there are still some noise samples remaining. The filter needs some space to compute the statistics, and as you are moving, the statistics are changing. But some parts it cannot adapt well. You need to have some local stationarity for the filter to adapt. And then if the statistics change slowly, it'll work. If the statistics change rapidly, then the filter may not be able to adapt. Still, this is better than that. Let's look at the RMS value. What does it say? Wiener is 52 and local is 13. So this certainly has lower mean squared error. E is a Wiener filter, that's 52. And this is 13. So the error is reduced compared to the noisy one. How much is the noisy one? 19. So the Wiener filter, because of blurring, has actually increased it. But I would say that's because of an inappropriate model I have put in. Okay? 12:30. Any questions before we go for lunch? Thank you.
For example, there are very G shapes are there. The natural image.
Yeah, true.
Yes.
Do I have any other example? I may have some examples later.
Capsicum images.
Yeah, those capsicum peppers images and so on. That I'll show you that. There are some real images. Well, they are also not real. They are stacked. So if you want, you can try that. I don't have any Wiener filter applied to medical images. I do actually in chapter on the nuclear medicine restoration. I do have some If you look at the restoration chapter, I won't go through that, but if you're interested, I can show you. We have Wiener and a few other filters, including Kalman filter for nuclear medicine images. So I can show you that later if you wish. These images, yes, true. We synthesize them that way, we design them that way in order to demonstrate the effects where filters work and where filters fail, where you get good results and where you don't get good results, and where you have these sharp edges, they pose problems. Will you have a real image like that? Maybe. If I'm taking a picture of this, there are these lines and sharp, all these tables and metal parts. There are some rapid transitions. So you may encounter such edges in sort of real images. So what's a real image? Maybe just my face just this much, but even then I have all these black and white parts, and if you apply some other makeup, then there'll be more rapid transitions. So yeah, there are such transitions in real life images. If you take only this much, maybe there is no variation. But those are sharp. No questions? Okay.